So you'll remember from your Unit 1 course that we covered polymers. You know that a polymer is made of smaller units known as monomers, and the way they are arranged and what those monomers contain dictate what the polymer is. Now, if you don't remember the basics of polymers, then do have a look at my Unit 1 videos, but we are going to move on now into the properties of various different polymers and what affects them. And so the first one really is going to be which monomer we have. So the monomer. The monomer, of course, if we had ethene and we were making polyethene, then that is going to have a certain characteristic. One example is nylon. Nylon can be made into fibers, but it's very strong. Climbers use it in their ropes in order to stop them from obviously falling off the mountain, and therefore it needs to have a really high tensile strength. So nylon is very strong, and the reason being it has two different monomers. And one of the monomers is acidic, so acidic, plus the other monomer is basic. So remember, acid plus base, you're going to get a reaction. And so the two monomers are bound together, and the fact that it's an acid plus a base, which really want to react with each other anyway, makes it a really strong bond and makes it hard to break. And so nylon is made of these two monomers. Okay, so that's one basic example of why the monomer is going to dictate the properties of your polymer. Next, we have something which is slightly less obvious, which is the reaction conditions. Reaction conditions. Okay, and the example we're going to use this time is ethene. So ethene, which of course makes polythene or polyethene. They're the same thing. If you were to write polyethene, then you put brackets in, and you would write polyethene like that. This is the correct chemical way of writing. Now I'm going to use a separate page so we've got more room in order to explain this example. So, polyethene can be found in two types. Polyethene is found in two types, and they are low density and high density. High density. And now, if you think of a polymer being a simple chain, if you like, of monomers. So let's say, for example, we've got loads of ethene molecules and they're going to join up, and then we just get this chain like that. And we're going to say that this just represents a big long chain of molecules, okay? The reason it's drawn like this is because it's not ever perfectly a straight line, but you don't need to go into that too much. Okay, so if one polyethene molecule looks like this, then what's the difference between high density and low density? So low density and high density ethene. Well, to demonstrate, I'm going to draw a box for each one. So let's pretend that these boxes are exactly the same size. They're pretty close. In low density polyethene, we have branching occurring. And so we have molecules of ethene which look like this. And then they might branch off like this. Then we'll have another one down here, and that will have branches as well. Branches like that, branches like this. You'll have another one like this. You'll have branches, branches. And if you see, these branches are stopping them from perfectly lining up. And so let's just draw one more down here very quickly. There we go. These branches are stopping them perfectly lining up with each other, because obviously the branches can't hit each other and they can't overlap, if you like. So that means that we have these molecules which are sort of separated, and what's in between them is empty space. If there's empty space in between them, that means that this inside this box is not very dense, because if we had loads of ethene molecules all layered, then that would be really dense. So this is why we call it low density polyethene. On the contrary, if we have high density polyethene, they are not branched, or barely branched. So we might have molecules like this. And if you have a look, if we had another molecule, it could pretty much line up with the shape of the one above, like that. And we can keep doing this all day long, like this. Even if you have them going in a different direction, like this, then other ones are also going to line up in that direction, over here, over here, over here. And you get the picture. We have layers forming. And how many molecules fit into this left-hand box? Well, 1, 2, 3, 4. How many, and I haven't even filled the box, which I could carry on and carry on like so. How many fit in here? Well, it's definitely more than 4. And that is why we call this one high-density polyethylene, and this one low-density polyethylene. Okay, and the reason we form these two separate types of polyethylene is basically the reaction conditions. So the conditions to form low-density polyethylene are high pressure. So we put it under immensely high pressure. Okay, and there is also oxygen. So it's only a little bit, so we say a trace of oxygen, but there is oxygen in there as well. And this will cause the ethene or the polyethylene to form branches. Now, on the contrary, if we have a slightly high pressure, so when I say slightly high, it's just slightly above normal, but it's nowhere near as high as this one. So slightly high pressure and only 50 degrees Celsius plus a catalyst. Now remember, a catalyst is something that allows a reaction to occur faster and at a lower activation energy. So if we include a catalyst and use these conditions, we are going to form high density polyethylene. And so these separate conditions, using exactly the same monomer, form two very different substances. And the low density polyethylene is obviously a lot weaker than the high density, because the high density polyethylene has a lot more of the polyethylene molecules in there. And so it is the conditions which allow ethene to form these two different types of polyethylene. So you have your high density and your low density. Now finally, we have two separate types of polymers known as thermosoftening and thermosetting. Do them in a separate colour so you can realise these are types of polymers, not just how we form polymers. Thermosoftening and thermosetting. Now, a thermosoftening polymer is one which will quite easily melt. So it will easily melt when we heat it, and then when we want to, if we want to reshape it, then we can remold them. So you can remold them into whatever shape you like. A thermosetting polymer is way stronger. It resists heat a lot more. So it doesn't melt easily. We'd have to raise it to a really high temperature. Doesn't melt easily, and so cannot reshape. Now that's important because if we want a plastic that we can keep reusing and reshaping, then a thermosetting polymer would be no good. Whereas if we want a plastic which is going to resist heat, for example our plug sockets, if our plugs heat up, if the plug socket decided to melt, then that's obviously going to be very dangerous and it's no good to us whatsoever. So for a plug socket, we would need a thermosetting polymer. Okay, so let's quickly have a look at a diagram of the molecular structure of these two. Okay, so a thermosoftening will be made up of polymer chains, like what we saw with polyethylene, like this, okay? And they become tangled up. So some might go like this, and you can see that they are starting to interlink with each other. Like this, and this is characteristic of a thermosoftening polymer. A thermosetting polymer, however, will not look like that. It may have molecules the same, these polymer chains, but there will be strong linkages between the two. And these linkages are covalent bonds. It's important to remember that a polymer is linked, each molecule is made up of covalent bonds. So if you remember with ethene, let's say polyethylene, it looked like this. So you'd have covalent bonds linking each of the monomers. I'm not going to draw the hydrogens in for now to save time, but this bond here is linking the two monomers, and this bond is a covalent bond, just like the rest of the covalent bonds in these molecules. Now, in a thermosetting polymer, this bond here is also a covalent bond. So the interaction between this molecule and this molecule is extremely strong, because we know that covalent bonds are very strong. However, if we take a look at our thermosoftening polymer, these two are just tangled up. Let's show a different colour. These two are just tangled up here. And we've got tangles here, and we've got tangles here, but there's no covalent bonds between this molecule and this molecule. No covalent bonds between this molecule and this molecule. And that means when we melt them, all we do is separate this one from this one and this one from this one, and that's really relatively easy because they're not covalently bound together. A thermosetting polymer, we need to break this covalent bond in order to separate them, and that obviously becomes very difficult. And with a lot of thermosetting polymers, they won't even melt. Once you heat them to a high enough temperature, they will do something known as charring. And you don't need to know this, but charring is actually an example of incomplete combustion. So we've looked at that before in Unit 1, but the incomplete combustion will cause residue to be left over. And so if you've ever seen a plastic be heated and you get gas given off, and then you get a black solid on the plastic, that is char, and it is carbon from incomplete combustion. Okay, so that's the difference between thermosoftening and thermosetting plastics and polymers. Going back to our flow diagram, thermosoftening and thermosetting polymers are useful for a variety of different things. What also gives a polymer its characteristics is the monomer you are using and the reaction conditions in which you produce that polymer. And so I'm going to stop here. That has been an overview of polymers, and I've given examples as well. If you do have any questions, then do please send me an email using the link below, or post a comment and I'll be sure to get back to you. But I look forward to seeing you in the next video.